Okay, so this is being recorded. You can see my screen, I guess, right? My iPad.
Yes.
Yeah.
Yes, we can.
If you can hear me, if there is any problem, you just let me know. All right. So last time we spoke about black holes. We looked at the metric very briefly, right? So just go a quick recap. We looked at the metric, and then we ask ourselves, okay, what happens to a light that is going on a radial null direction? So radial null, so that means that it goes in straight lines. And we saw that in principle, it's going to take it an infinite amount of time to reach the Schwarzschild radius, 2GM. We said this in a way is an artifact. I mean, it's not an artifact in the basic sense that, if I'm an astronaut and you're an astronaut and you decide to go into the event horizon, the Schwarzschild radius, then I will never be able to see you reach there. I mean, it will always take an infinite amount of time from my clock to see you. Doesn't mean that you will never be able to reach there. You will, but I will never be able to see because what I'll say is that you're getting, it takes you longer and longer time as you approach. And of course, you're getting redder and redder as you approach it. But we say in reality, this is not going to happen. What's going to happen is that you will reach it. So reality is I will never see you, but it doesn't mean you couldn't reach there. And then we simply played some game and started to play with the coordinates, saying, okay, what happens if we change coordinates from TR to some other coordinate? So we define R star as a 2 coordinate. And basically what this did was just to throw that Schwarzschild radius to minus infinity. And then we continued to play with that, and we introduced the Eddington-Finkelstein coordinates when we switched T to U tilde. And when we did that, we found out that there is really no problem entering the horizon. So R equal to GM is the horizon in these new coordinates. But then we got some very nice result that if you enter the horizon, you never are able to get back. It's a one-way ticket. And in fact, all future directions will take you towards R equal to 0. This is the place where all the physics is gone. So we don't really know what happens there. Just slightly before that, um, the laws of physics as we know them fail to exist. And then we said, okay, that's why it's called the event horizon. So there could be some events happening there at R smaller than 2GM. Things could happen, but there is no way for us to know. But yeah, they're not going to take very long to happen because anyway, all the future directions will take you to the singularity at R equal to 0. So that's the origin of the name black hole, since light cannot escape. But then we saw that, we broke the symmetry in somewhat arbitrary way, which we chose U tilde. We could have chosen V tilde, and then we get exactly the opposite. So we get a white hole. Then we asked, how can that be? What really happens here? And we said that in reality, it takes infinite amount of my time as an observer to reach the black hole. That means it will take infinite amount from my time minus infinity to get out of this white hole. And of course, since the universe, as we're going to start learning today, is only finite in time, then this is not a real solution, right? Because we're still talking about Schwarzschild solution, in vacuum. And then we continued to play and we introduced the new coordinates, the Kruskal coordinates, or Kruskal-Sekkers coordinates, which are normally U and V. And in normal textbooks, modern textbooks, I've seen more and more of these capital T and capital R rather than U and V. And in these coordinates, the entire space can be divided into 4 regimes. The region one, which is the region where we are, there is no problem. Region 2 is what we call the black hole. Region 4 is what we call the white hole, and there is region 3, which is basically a symmetric region to our region, symmetric universe, which we have got no way of reaching. So it's a mathematically correct description, but physically it is meaningless because there is no way we can get there. But it's good for science fiction movies. All right, I think that's as far as we managed to go to last time. So before we start a new subject, I would like to stop you and ask you if you have any questions to me.
So third region, it's like wormhole.
Yes, in principle, to get from region 1 to region 3, what you need is a wormhole. What you really need is a way of being able to travel faster than light.
Mm-hmm.
Since there are no known particles in nature that can travel faster than light, then there is no way to communicate between these regimes.
Yeah, but there is only one point which connects first and third region, it's singularity, and
In this
probably
coordinate
somehow, yeah,
in this coordinate system, right? We discussed this
yes,
coordinate system. The lines, the brown lines here represent constant time, right? And this line here represents time goes to infinity, right? So yeah, I mean, in this coordinate system, this region exists, but it's physically it's meaningless in the sense that there is no way for us to reach there. Okay, but mathematically, mathematicians can do many things. Mathematically, it's there. I have to tell you it's there. Okay. So if everything is clear, we're going to start today the last subject of the semester, which is called cosmology. Let me just a little bit so it will be easier for me to write down. Cosmology. So, with Einstein's equation is the basis for study of modern day, many objects. I mean, black hole is an object. We didn't speak about neutron stars in the equation of state. We didn't speak about other objects. But in addition to the study of different objects, there is a study of the global structure of the universe as a whole. Okay, and this is called cosmology. So it's basically considered a field of itself. I mean, there are people who are called astronomers or astrophysicists, and there are people who are called cosmologists. This is an independent subfield of people that do research in this area. So this is called the study of the universe on the largest scale is called cosmology. So cosmologists are not interested in the, objects such as stars or galaxies or black holes. They're interested in the properties and evolution of the universe as a whole, right? And modern day cosmology is based on what we call a cosmological principle. And the cosmological principle, we have to go back. It's based on the idea of Copernicus, which is called the Copernican principle. And what did Copernicus said? This is something which I guess you know. What was the great, achievement of Copernicus?
You mean the statement that we are not in the center of the universe?
Exactly, right? The Copernicus says that the Earth, prior to Copernicus, people believed that we are at the center of the universe and everything is surrounding us, right? Copernicus was the first to say, actually, we're not. We are orbiting the sun as the Earth. So the idea that that's called the Copernican principle. Principle says that the Earth is not the center of the universe. Which, most people older than the age of 5 understand. And the modern day cosmological principle states essentially the same. It says that the universe on a large scale is homogeneous and isotropic. Namely, that there is nothing special in our place in the universe. Okay, so that's called the cosmological principle. Cosmological which is, a modern day version of the Copernican principle. It states that the universe at a large enough scale, the universe is homogeneous without an S, and isotropic. So what is homogeneous?
The density of matter is around the same across
Is the same everywhere,
universe.
yes. Yes. And what is isotropic?
Direction the same. I mean,
Everywhere we look, it's the same, exactly. Now, of course, this is wrong, right? I mean, if I look to my left and I look to my right, I don't see the same thing. So obviously, I cannot say that the world that I'm surrounded by is isotropic. And also, the conditions right here in your room and the condition at the center of the sun are not the same. So obviously, it's not true to say that the universe is homogeneous, right? Things do evolve. But we believe that on a very large scale, so we're not talking about the scale of the solar system, not even the scale of galaxy, not even scale of clusters of galaxies. We believe that on a very large scale, scales that are larger than scales of clusters of galaxies, this is a very good approximation. Okay, so we believe that this is so on a very large clusters of galaxies. Scale. Why do we believe that? I mean, this is science. It's not about belief. Why do we think so? So there are various hints that tell us that, right? So a few is that, when there are surveys that look at galaxies around the sky, right? The distant galaxies. And when you look at surveys of galaxies, you're saying that they are roughly homogeneous and isotropic in the far universe, right? So we're talking about number counts of galaxies, evidence. Let's call it evidence, although these are suggestions. Number counts of galaxies. Then we also have diffusive X-rays and gamma rays radiation. Diffusive X and gamma ray radiation. And of course, the most important, which I'm sure you've heard of, you don't know what I'm talking about?
maybe Big Bang? No?
We haven't reached the Big Bang yet.
Okay.
We are not there yet. We'll get there. But this will only be next week, I think. No idea? CMB tells you something?
Yes.
Yeah, so CMB is cosmic microwave background.
Mm-hmm.
What is this CMB?
Well, it's like very homogeneous and very constant noise, like background radiation all over the place.
Exactly. So it's a 2.7 degrees Kelvin, very, 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 very cold radiation that surrounds us all. And it's homogeneous and isotropic. It was discovered in the 1960s. Now, you don't know that, I guess, because when I was a child, there was televisions which were antennas. Sometimes you can see still antennas, right? Because then the broadcast of television was not done via cables, but was done via transmission, radio transmissions. And then if the antenna was not properly adjusted, then there will be some background noise. You might know that it looks like a snow. You just call it snow. I guess maybe you're too young for these things. When I was a kid, this was the way it was. So this is not a coincidence. I mean, this is 2.7 degrees radiation that surrounds us all everywhere in the universe. And it's nearly completely isotropic. It's not exactly isotropic. There are small fluctuations in there, and they tell us a lot. I don't think we'll have time to discuss that. Maybe towards the end, it tells us a lot about the content of the universe. I maybe in the last lecture, I'll mention how we can learn from that. But it's a very tiny fluctuations of the order of 10 to the minus 5. So delta t over t is of the order of 10 to the minus 5. So generally, it's pretty homogeneous. And that's around us all. It's not exactly homogeneous. Do you know why? It would have been homogeneous.
Maybe quantum fluctuation. It's
No, something much simpler than that. If we were what's called co-moving, so if we're just steady, it would be completely homogeneous. But because the Earth itself is moving around the sun, and the sun itself is moving around the galaxy, and the galaxy itself is moving, then we do see the dipole because of the motion of the relative motion of us relative to this background radiation. Okay, but this still is a very small deflection, something like 10 to the minus 3, so it doesn't really matter. So, okay, so that's the basic idea. Now, a little bit of formalities before we're going to do some algebra today. I hope I'm not going to disappoint you too much. It is an algebra really, and the reason is because I don't want to just throw you away the things. I want to show you that the full mathematical proof of them. But formally, when we speak about homogeneous, that means that there are any 2 points, homogeneity, formality. Any 2 points, P and Q on the manifold M, then there is an isometry. So for any 2 points, there is an isometry from P to Q. Can you think of a metric that is isotropic but not homogeneous? Anybody?
Maybe Schwarzschild metric. We can only rotate it, and
Actually, yes. Actually,
stay
yes.
the same and
Right.
move
Yeah,
time, but
think of a cone, right? If you have a cone, you're sitting right here, you're saying it's isotropic, but obviously it's not homogeneous. And the Schwarzschild is also a very good example. What about homogeneous and not isotropic? Yes, if there is a preferred direction, if you have something that goes like that. If you're in the middle of the sea and there is a wind that takes you in one direction. That's not homogeneous and not isotropic. But then again, there is a mathematical statement that states that if the space is isotropic everywhere, then it's also homogeneous. Also, if it is isotropic or if a space is isotropic around one point and is homogeneous, then what? Then it's also isotropic.
It's
Sorry?
isotropic and homogeneous in the vicinity of the point.
Yeah. Isotropic everywhere.
Okay.
Okay, so think a little bit about that. It's not too complicated. It's just two different terms. Okay, what else I want to say? So obviously, we cannot tell if it's homogeneous everywhere. But from our perspective, there is plenty of evidence that it is isotropic. So data, right, these are observations, say we have it isotropic here where we are, right, from our point of view. And then we have to use the Copernican principle which again states that we are not at the center of the universe. That results in isotropic everywhere. Now, if we have a space that is both homogeneous and isotropic, it has a name. Such a space, do you know what it is? What do we call a space that is both homogeneous and isotropic?
Perfect space.
Yeah, very close. That's called a maximally symmetric space. Now, so basically what we're going to do now is we're going to study the properties of maximally symmetric spaces. Right, the mathematical properties I told you today, we'll do still some algebra. This is the last more serious algebra that we have during this course. But there is one caveat here. Right? When we look at distant galaxies, what do we see? Well, you might have, I'm pretty sure you've heard that.
Well, the farther away from us, they're like accelerating and moving
Yeah.
away from us faster.
Away, right. They're receding away. The term in English is receding, right? They go away from us. So they do change in time, which means that the universe, that's of course Hubble's discovery, right? So the universe is not static, right? It is changing in time. Hubble showed us that the universe is not static. But changes with time. So that means that the idea that the universe is homogeneous and isotropic is only applied for the spatial part of the universe, okay? Not to the temporal part. So we'll have to make a distinction. Remember when I introduced the notation of 4 vectors at the beginning of the semester, I told you that when we reach cosmology, then we'll have to make the separation between time and space. So the spatial part of the universe is homogeneous and isotropic. But the temporal part of the universe is not, is evolving. Okay? So really, technically, what we speak about is called the maximally symmetric subspace of a 4-dimensional space. Okay? So from a mathematical perspective, that's what that is the meaning. Right? So it's a maximally symmetric subspace. For our purpose, it doesn't really matter, but if you think of it from a more inclined into mathematical perspective, then you should be aware of these subtleties. Okay. Now, what we're going to do is to derive the metric that describes this universe. So so universe that evolves in time but has a maximally symmetric spatial subspace. The metric is called the Robertson-Walker metric. So a metric that describes a universe or space, doesn't matter. Space-time with a maximally symmetric spatial part is the Robertson-Walker metric. So what we're going to do, we're going to first derive this metric from general considerations of maximally symmetric spaces. Then we're going to use this metric into Einstein's equation. Now, this time it's not going to be Einstein's equation in vacuum as we did for black holes, because the universe is not empty. There are things in the universe, obviously. So we'll have to introduce Einstein's equation under the stress energy tensor, the right-hand side of Einstein's equation, which of course will be derived in a simple way. And what simplifies it is the assumption of homogeneity and isotropy. And then the result is called Friedman-Robertson-Walker metric, or Friedman-Robertson-Walker universe, not metric. The metric is Robertson-Walker. Okay. Then we will derive the Friedman-Robertson-Walker universe, and we'll study the properties of this universe. And you'll see it will lead us to the concept of the Big Bang and Hubble's law and other things that you have heard, but likely never learned properly. Oops, what happened? Why? What happened? What is it open now? Can you see? Okay, there was Maybe I touched the cable or something. Okay, can you see it now? You're all muted, so I cannot hear you.
Yes, yes.
Yes, yes, you can see it.
Asaf, may I ask you a question?
Yes.
Before we go further, I have a question about, do people know where is the center of the universe, or the universe doesn't have any center?
Well, that's the thing. There is no center, right? There is no center. That's the whole thing.
Mm-hmm.
Can
But
you?
I mean, people prove it somehow that there is no center, or
We're
it's
going to
our
prove.
belief.
When we say it's homogeneous and isotropic, and then there is no center. I'm going to ask you a question, right? If you're looking at the surface of the Earth as a surface, not as the Earth, right? The surface of the Earth, can you define a center to the surface of the Earth? Can you say that one point is more central than any other point?
No.
No. So it's exactly the same thing, right? I mean, somebody can say, okay, the center of the surface, I don't know, Jerusalem, whatever. If you want to believe it, that's fine. But there is no real reason to choose any point on the surface of the Earth more than another point.
But I mean, if we look at Earth as not a 2D object, but as 3D object, we know exactly that there is a center, right?
Well, but then you're looking at the surface, but I'm talking now about only the surface, or the 2D surface. So, the same thing for the universe, right? We're not assuming that the universe is embedded in any higher dimensional space. When we look at the universe by itself, right, there is no center to the universe. There cannot be any. After we derive the Friedman-Robertson metric and we start to describe the properties, sorry, the Robertson-Walker, we don't need the Friedman for that, then you'll see what it means. I mean, there is no, but I already gave you basically the intuitive answer.
The metric will not have any singularities.
No, cannot have any singularities of such a metric. It has to be homogeneous and isotropic, right? So as opposed to the Schwarzschild, which does have a singularity, we're talking here about an isotropic and homogeneous universe. So clearly there is no singularity in that metric.
Okay, thank you.
One thing at a time. We'll see, we'll get that. But yes, I mean, you're starting to see that it's conceptually, it's very different than the Schwarzschild solution. It's still a solution, but it simply describes something else. So now what we're going to speak about is a maximally symmetric spaces. And I told you today we're going to have some more algebra. So don't get annoyed by that. There is a good purpose for that, right? Okay. So technically, how do I define a maximally symmetric space? I think by now you should know the answer.
It is isotropic and homogeneous. Now
let's talk in a mathematical way. Formally, a maximally symmetric space.
It has like continuous symmetry in each one of its coordinates.
Try harder. Is a space of what? What can I say about a maximally symmetric space?
It has a continuous symmetry in each one of its coordinates.
Maybe it has the maximum number of Killing vectors.
That will be what we're looking for, right? A space that possesses the maximal number of Killing vectors. Which is essentially what you're saying, right? I mean, a Killing vector represents a symmetry, right? Isometry in one direction. So the maximum What is the possible maximum number? If we have an n-dimensional manifold.
N multiplied by n plus 1 divided by 2.
Exactly. This will be n plus 1 divided by 2. Why? Why this is the number? Okay, if it's a Euclidean space, right? If it's
This is
Euclidean,
like,
yeah.
if I think of a matrix, it's like the top triangle, 3 elements.
Okay, yes, but I want to get the physical insight here. So if we have a simple one, right? Euclidean, Rn, Euclidean space Rn. I'm not going to give you the full proof, but the idea is exactly the same. If we have Rn, how many killing vectors we have? I mean, what do the killing vectors represent, right?
We have n translations,
Exactly. So we have translations,
rotations.
stations. So translations, obviously, they're n. I can go in n directions. And rotations, I have n times n minus 1 over 2, right? For each dimension n, I can do n minus 1 rotations and divide by 2 because I don't want to double count, right? I can do around the x-axis, I can do a rotation in the y-z, also around the zy, so I don't want to overcount them, right? So n overall, n plus n minus 1 over 2 is n times n plus 1 over 2, right? So Euclidean, think of Euclidean flat space, that's easy. But if I would do a sphere, right, it would be exactly the same thing. Just slightly different way of thinking, but you get the same thing. Right? Okay, good. This would be the total number of independent killing vectors. And I think it appeared in your homework already, right? So if n is greater than or equal than 2, then there are more killing vectors than dimensions. Right. Of course, killing vector field defined everywhere, not only at a point. If it was just a point, we couldn't do that. But because they're defined everywhere, then the coefficients are different. So that's an intuitive reason why it is so. Okay, so in order to proceed, what we're going to do now, this is the mathematical part that I promised you. I want to derive the metric. What I want, I'm going to do the next half an hour or so will be more mathematic. We're going to go through a few more algebraic properties of the killing vectors that we have not discussed so far. So a few more algebraic properties of killing vectors. Okay. So let's go over it. So we start by the fact that the killing vector satisfies the killing condition, right? So obviously K killing condition. K is going to be a killing vector. So K sigma rho plus K rho sigma is equal to 0. Now, remember from the definition of the curvature tensor. if we have any two vectors, doesn't have to be a Killing, but any vectors, in particularly Killing, then the commutator, now use mu. Just want to be consistent with myself because it's going to be confusing anyway. Okay, sigma, it's any vector, which is a what? This is a k sigma rho mu minus k sigma mu rho is equal to minus r lambda sigma rho mu k lambda. All right, we derive this. This is not true only for Killing vectors. This is true for any vector from the definition of the curvature tensor. If you don't believe me, go back to the part that we discussed curvature. Yeah? You believe me, or you're just nodding your head that you believe me?
Yeah, it's fine.
Okay, it's fine, yeah. Okay, now we also had the cyclic sum rule, the curvature tensor. Which was r lambda sigma rho mu plus r lambda mu sigma rho plus r lambda rho mu sigma is equal to 0. Right? We had that. Then we can use that in here. Can merge them together. Right? And I just get here that, okay, I'm just basically copying that by using the sum rule. So we end up with a k sigma rho mu minus k sigma mu rho plus k mu sigma rho minus k mu rho sigma plus k rho mu sigma minus k rho sigma mu is equal to 0. Okay, I just switched the I did a cyclic sum over the sigma rho and mu, using the fact that the cyclic sum rule implies that this has to be equal to 0. Okay. Now we're using again the Killing condition, which is here. So this, this would be a minus. I can switch that. Right? And I get the same. So I get twice the first one. And the same I have for these two. And the same I have for these two. Right? Just using the Killing condition here. And so I end up with a k sigma rho mu minus k sigma mu rho minus k mu rho sigma is equal to 0. And then I can use that again in here. Right? K sigma rho mu minus k sigma mu rho is a minus that. So I can write that as k mu rho sigma equal to minus r lambda sigma rho mu k lambda. Okay, it's algebra. I just have to follow closely all the terms, but I did not use anything we have not seen already. Okay. Okay, some parts are true. In general, some parts are true because I use the Killing condition. So that is one result which I'm going to use. No,
can you
yes.
repeat again, please, why the first term and the last term are the same?
What do you mean the first term and the last term are the same?
When you apply the cyclic sum rule to the
This one here?
yes, the upper line. Yeah.
K sigma rho mu minus K rho sigma mu, first and last
Yes.
one. But
Yes.
I'm using the killing condition. So minus K rho sigma mu is a plus K sigma rho mu. So I can switch that, right?
Okay.
Minus. So I have it twice.
Mm-hmm.
Really, there should be in here, there should be a 2 multiplied by all of that.
Okay.
Okay. So this term, the last term, and the first term and the last term, can you see it? I don't know. I don't want to play with that, so it's not going to make any troubles. But the first term and the last term are, actually twice the first term. And then these two are twice are twice as well, and these two are also twice. So really there is 2 written here, multiplying everything.
So from this line, we begin to use that we are working with not abstract vector, but with Killer vectors, right?
I could not understand your question. I'm sorry.
From this line, we begin to use that we working with not arbitrary vectors, but with killing vectors, right?
Yes.
And apply all the conditions and
There's only one condition. It's a killing condition.
okay.
Not what I did here. I started with the killing condition, right? So I started with the killing condition here. Then I use a property of the Riemann tensor and the sum of the Riemann tensor. That's all I did. Okay. And then I just wrote it down. This would be a 1, this would be 2, and this would be 3. So I use 2 and 3 together to write down this equation here. And then I just use the killing condition again to reduce it to that equation. And then I wrote it again using, I wrote equation 2 again using that equation. So this is really equation 2, that is written here, which is derived directly from the property of the curvature tensor. Okay. Yeah. You with me?
Yeah, thank you.
Okay. Now I'm going to do the same using again the definition of the curvature tensor. Now for taking another derivative, another commutator. So now I'm going to take an extra term. So again, from the definition of the curvature, is a K rho mu sigma nu minus K rho mu nu sigma this is a minus R lambda rho sigma nu K lambda and mu minus R lambda mu sigma nu K rho lambda. So that again, I took the commutator of K rho mu, which is a 1, 1 tensor, sorry, 0, 2 tensor. And so I got these 2 terms here. Again, go back to the definition of the Riemann tensor. Now, we take this equation from here, and we want to use these two equations combined. So I take the derivative, and I replace mu with rho. In this equation, so I get k rho mu sigma is minus r lambda sigma rho mu k lambda. And when I take the derivative, I get that k rho mu sigma nu is a minus r lambda sigma rho mu nu k lambda minus r lambda sigma mu rho k lambda nu. Okay? You follow? Follow the algebra? And thus you don't seem happy?
No, it's okay. It is what it is.
What it is, yes. Okay, I told you there will be some algebra, but not too much left, actually. Okay, no, there is some more left. There is a reason why I do that, and the reason is unclear just because I want you to believe me that I'm not just cheating on you. I'm really doing, the metric I'm going to, we're deriving the metric, basically. So now we do the same by now replacing sigma and rho and nu, sorry. Place sigma and nu, and then we got that k rho mu sigma nu minus k rho mu nu sigma, right? Which is what we have here, right? Is equal to a minus r lambda sigma rho mu nu k lambda minus r lambda sigma mu rho k lambda nu. What did I do here? Should be a lambda, right? Yeah. Plus r lambda nu mu rho sigma k lambda minus r, sorry, plus r. Yeah, I switch here the order to put the plus r lambda nu mu rho k lambda sigma. So I did an exchange of the last two indices to change the sign. So using this result in here, we can write down that r lambda sigma rho mu k lambda nu minus r lambda nu rho mu k lambda sigma plus r lambda sigma rho mu nu minus r lambda nu rho mu sigma times k lambda is equal to minus r lambda rho sigma nu k lambda mu minus r lambda mu sigma nu K rho lambda. So again, using the Killing equation. Okay, this is just continuation of what we did here. I just wrote down this equation and using that result I have here. Okay. Now I'm using again the Killing equation. So K Killing equation alpha lambda is a minus K lambda alpha. And alpha is everything from sigma nu rho. Then we end up with some minus R lambda rho sigma nu delta kappa mu plus R lambda mu sigma nu delta kappa rho minus R lambda sigma rho mu delta kappa nu plus R lambda nu rho mu delta kappa sigma, all that multiplied by K lambda kappa is equal to R lambda sigma rho mu nu minus R lambda nu rho mu sigma kappa lambda. Okay, I admit this is not the most fun thing that you can think of, but I wanted to derive this algebraic property, which is true for any Killing vector. And I needed that one. Okay. I won't say it's nice. I just say it's straightforward. It's just a basic algebra, which I did not use anything beyond the properties of the Riemann tensor and the properties of a Killing vector. So it's pretty much straightforward to derive it. Now, have in mind that I did not have yet any look about maximally symmetric spaces. I just said these are general properties of a Killing vector. Questions about that, the derivation?
No.
Again, it's straightforward. I can tell you about this derivation. I didn't see it appear. I mean, a similar derivation appear in many textbooks, but each one actually does it in a slightly different way. So if you look at different textbooks, you'll see they all end up with this equation, but everybody is deriving it in a slightly different way. This way for me was the easiest to follow, and I think it's easier to get. Everybody has its own. I'm not sure even why, but every textbook has some slightly different derivation of that. Okay. Now let's look at maximally symmetric spaces. So values of Killing vectors at any point in space-time. First, have a look at what we have here. Before we even begin, look at this equation here. And at this equation here. Right? Let's say that we know the value of the Killing vector and its first derivative at some point x, space-time. right? So we know k lambda, right? That's the killing vector, and we know, I cannot see, we know k lambda, and we know the derivative of k lambda, right? So from this equation, we have that the second derivative is also known. Right? This is the vector k lambda. This is the first derivative of k lambda here, right? It's the first derivative of k lambda. And this equation here tells us that the second derivative is also known of k lambda, and this equation tells us the third derivative is also known, right? And we can keep on forever. So if we happen to know the value of k and its first derivative in any point in space-time, right? That means that we can find the value of k in any nearby point, because we can extend this derivatives forever, basically. Yeah? If we know k lambda at x and k lambda nu at x, we can use Taylor series to find k lambda at any nearby point x1. So k, whatever. Row, because we have n of those, at x1 is a row lambda x1 x plus, sorry, times k lambda n at x plus b row lambda nu at x1 even x k lambda nu and at x. N is for different killing vectors. Okay. The function,
why we don't use the high derivatives?
because we don't need. They will be, because if I know what k and the first derivative of k, I know all the derivatives of k. So it's enough for me to know, right, from here, I know all the derivative of k. So it's enough for me to know the value of k and the first derivative of k, and everything else will enter into these functions a and b, right? So a and b, the functions a row lambda and b row lambda nu depend on the metric and on the location and x, but not on the initial killing vectors, right? But not on k lambda x. Okay, I don't need to go on forever because everything else is already set once I know the killing vector and its first derivative. I mean, I could write here in other terms, but these terms will be automatically determined by the A and B. They're not independent.
Why the first term of the Taylor expansion, I mean, the Killing vector has lower index nu instead of lambda?
Where? Here it's a lambda. Sorry.
Okay.
I didn't write it properly, I'm sorry. Still, my handwriting is not the best, especially when it is electronic.
But how can you find this A and B functions? You just plug it into the equation above? Okay.
Hold on. In principle, yes. I mean, this is conceptually, you can see it conceptually because of that connection, which is marked here, right? I do not need, I mean, I can do a Taylor expansion, but I do not need infinite number because I can only do with the first two terms, I determine everything. Okay, now, okay, now we said these functions depend on the metric and on x. They don't depend on the k nu or the derivative k nu lambda. Sorry, k lambda nu. So these are the same for all Killing vectors. They are the same for all Killing vectors. So that's another proof that we can have only n plus 1 over 2 independent Killing vectors. Now, finally, we can talk about maximally symmetric spaces, right? Killing vectors in maximally symmetric spaces. So remember that maximally symmetric space is both homogeneous and isotropic. So consider a point X in a homogeneous space. So we have total in n-dimensional space, goodness, and dimension space, right? So we have total, you should write it down, actually, it's capital N. Okay, so we have total of n Killing vectors. Independent Killing vectors. I should start in a different way. Consider a different, okay. Look at a different point. Look at a different point, arbitrary point, x1. So there is always a Killing vector between x and x1. Right. In n-dimensional space, there are total n independent Killing vectors. So I can mark them as k lambda and x and x1. Where n, now your small n is just, it's a sum, it's because I have total capital N killing vectors. So I can always choose these to be k lambda of n at point x to itself. I can simply write it as a delta function, right? Simply unity in all directions. Again, think of translation, right? If the space I would describe it in a Cartesian coordinate system, it will just be the directions.
Asaf,
Yeah.
can I ask you a question?
Yes.
Before, so why is there only n independent Hilbert vectors? Before we said that it's n multiplied by n plus 1 divided by 2.
I'm there. Second. I'm there. This is just for the translation from point x to x1.
Ah, okay.
Now you're right. Now comes the isotropic. So isotropy. So the homogeneity says that I can always take from one point to another. So these are the translations. So there are n such translations. Now we talk about isotropy, meaning that I can rotate, right? So what is an isotropy? That there is infinitesimal isometry. Isometry. Namely, x mu prime is x mu plus epsilon k mu. That leaves the point x fixed, right? If I rotate around the point itself is not changing, right? Such that k lambda of x is equal to 0. And its first derivative take any value. K lambda nu x. This is the first derivative. So if I write it, I would say that in n-dimensional space, I have n and m goes from 1 to n. Then we have that k lambda of n and m is equal to 0. K lambda rho of n and m, and this is the first derivative, is lambda rho k lambda n m from x1 and x, where x1 is equal to x. What would that be? It would just be the delta functions, delta lambda n, delta rho m, minus delta lambda m, delta rho n, which is, of course, minus k rho lambda and m at x, which is nothing but to say that the first derivative is antisymmetric. Okay, again, if this is confusing, and it is confusing because for me it took me a few minutes to get it. So I'm just, think of rotation, right? What do I do when I do rotation? Right? Infinitesimal rotation, that's exactly what happens, right? I'm just rotating. I take the point to itself, but the first derivative is being rotated, which is an epsilon, basically. Now that is true in any maximally symmetric space. So in any maximally symmetric space, at any given point, one can find Killing vectors such that k lambda is equal to 0 and k lambda nu is a minus k nu lambda. Now we're going to take these Killing vectors and plug them in the equation that we derived here. K lambda is equal to 0, meaning that all the right-hand side is equal to 0. So what we're going to get is minus, let's write it again, minus r lambda rho sigma nu delta kappa mu plus r lambda mu sigma nu delta kappa rho minus r lambda sigma rho mu delta kappa nu plus r lambda mu rho mu delta kappa sigma to 0. Okay, sorry, times k lambda kappa, lambda kappa. Now k lambda kappa is not 0. K lambda kappa is not 0, which means that the only way for that to be equal to 0 is if all these parentheses is equal to 0. So using that, so we now have the last two terms here. How am I going to write? I'm going to do a slight more algebra using the Killing condition. So minus r lambda sigma rho mu delta kappa nu plus r lambda mu rho mu delta kappa sigma times k lambda kappa. I'm going to use the Killing condition to write it as a minus r lambda sigma rho mu delta kappa nu plus r lambda nu rho mu delta kappa sigma k kappa lambda. So this is r lambda sigma rho mu delta kappa nu minus r lambda nu rho mu delta kappa sigma k kappa lambda. Now I'm going to switch. I'm not going to use Killing's equation. I'm just going to change the notation between lambda and kappa. Those are both Lama indices. So this is r kappa sigma rho mu delta lambda nu minus r lambda kappa, nu rho mu delta lambda sigma k lambda kappa. Now I can use that inside this equation here. Then down that minus r lambda rho sigma nu delta kappa mu plus r lambda mu sigma nu delta kappa rho plus r kappa sigma rho mu delta lambda nu minus R kappa nu rho mu delta lambda sigma is equal to 0. Now we are contract kappa mu. So what do I get here when I contract kappa nu? First term. What do we get?
Richard answer? No?
R lambda rho sigma nu and delta kappa nu. When I contract kappa and mu, what do I get? Cannot hear you if you're saying anything. What is the delta mu mu?
1.
1.
No. N R lambda rho sigma mu nu plus here I have contraction kappa and mu. So I get plus R lambda rho sigma nu minus R. Here I'm contracting lambda kappa and mu. I switch that and I simply get the Ricci. So minus R sigma rho delta lambda nu. Right, I just switch here the order, so I get the minus sign and then I contract, so I get the Ricci. And here it's pretty much the same, plus R nu rho and delta lambda sigma is equal to 0. Right? And dimensions, delta mu mu is n. Now we take that and multiply that by G lambda alpha. And then these two terms will be moved to the right. And we get n minus 1 R alpha rho sigma nu is equal to R nu rho. Let's switch the order. Here I have a G alpha sigma minus R sigma rho G alpha nu. Now, because of the symmetry of the Riemann, okay, this is anti-symmetric. It's exchange of alpha and rho. So we get that R nu rho G alpha sigma minus R sigma rho G alpha nu is a minus R nu alpha G rho sigma plus R sigma alpha G rho nu. And then we're nearly close to the end. We multiply that by G alpha lambda. And we get R nu rho G alpha sigma G alpha lambda minus R sigma rho G alpha nu G alpha lambda is equal to minus R nu alpha G rho sigma G alpha lambda plus R sigma alpha G rho nu G alpha lambda. And then we are contracting lambda and nu. And we get R sigma rho minus n r sigma rho is minus r lambda lambda g sigma rho plus r rho sigma. Okay, this should be quite straightforward to you if you manage to follow me all the way up here. Which means that we got that r sigma rho is 1 over n g sigma rho r lambda lambda. And then we use that in here. Write down that r lambda rho sigma nu is r alpha alpha over n minus 1 g nu rho g lambda sigma minus g sigma rho g lambda nu. And finally, if the space is isotropic or an isotropic space, we can use a Bianchi identity. Nabla mu, g mu nu is a nabla mu r mu nu minus 1/2 r g mu nu is equal to 0. Together with the definition that we have here. Yeah, that is 0 is r sigma rho minus 1/2 delta sigma rho r lambda lambda sigma. Which is 1 over n minus 1/2 r lambda lambda sigma. Okay. That was a bit lengthy, but I told you this is just an algebra. So if n is greater than 2, namely 3 dimensions, that means that r lambda lambda is constant. And if it's constant, then we can write down new constant, which we call k. So we write r lambda lambda is n minus 1 k. And with that, we have from here that r lambda rho sigma nu is some constant k times g nu rho g lambda sigma minus g sigma rho g lambda nu. Okay. And that's, sorry. And that is the equations that I wanted. So working very, very hard. You don't see it right away. I mean, we spent the last, I don't know, 1 hour playing with properties of Killing vectors and symmetric spaces in the Riemann tensor. And that's essentially what I wanted to get to, that in a maximally symmetric space, we can write the Riemann tensor as some constant multiplied by the metric components. And this is the result we're going to use. I think we won't do it now, but we're very close to derive to get the full Robertson-Walker metric from here. Okay, so I warned you that today will be more algebra, but this is really the last bit of algebra, of heavy algebra in the course. Of course, there's more algebra, but it's not very heavy. Questions, everybody? No.
I have a question about the last recording, where I can find it.
On the course webpage, it's already there.
Okay, on Lemida, right?
If you go to Lemida, whatever, go there. And there is on the left-hand side, there should be videos, and the video from last lecture is there. But I can't recall how much of that was in English and how much was in Hebrew, because I think all the students were Hebrew.
Yeah.
Anyway, it's there. And also my lecture notes on black holes and Schwarzschild metric are also in there. And I keep on, I told you and I keep on telling you, go to the literature. This material is obviously, I'm not inventing it. It's something which exists in every standard textbook about general relativity. All right. Okay, so I'll get the next problem set today. I think the last one will be next week. And I wish you all a quiet and happy weekend, as much as we can here. And then I will see you all on Sunday at 10 a.m. and it will be the same Zoom link. If you don't hear from me, just link to the same Zoom. We'll keep on doing the same thing as we're doing now. All right. So, but then now we have all. This was a mathematical tool that we needed to discuss the Robertson-Walker metric, and then we'll discuss the metric, and you'll see. It's going to be a lot of fun in this part of the course now. All right.
Okay, thank you.
Thank
Oh,
you.
thank you. Have a quiet and safe weekend. If you need anything from me that I can help you, if you need more extra time or anything, just tell me. I think just sit down and relax and do your homework and enjoy the material. All right.
Okay, thank you.
Oh, I can
Thank
do
you.
is
Have a good day.
stop
Bye.
recording. I hope.
Bye, thank you.
Do I do a stop recording?